Hello, good morning. I hope you guys are having a good day or whenever you're watching this. So we finished up our third chapter. We talked about quantitative data and did a lot of work with histograms, also box plots with 5-number summaries. Talked about different what's the difference between having skewed data and symmetric data. When we're able to use mean and standard deviation, we even calculated standard deviation by hand, which was really fun, filling in that table for 5 minutes or whatever. So thanks for bearing through me with that. I think it's good for you to understand how deviations work when we square deviations, and understanding how outliers cause standard deviations to get so big, because the deviations before we square them are going to be really, really large. All right, but what's more interesting than that is actually comparing distributions together. So looking at two different histograms or two different box plots or 5-number summaries, and being able to compare and contrast multiple distributions. So one way we can look at this is with average daily wind speeds. So up in, if you read the chapter, you can read about it. But anyway, there's a national park, I think in Vermont or something like that, up in the Northeast in New England. And one of the things that they do is they monitor the wind speeds, the average daily wind speed. So just to give you an idea what an average daily wind speed is, they use wind gauges, some scientific equipment like this. I just found that image on Google, and what they do is they actually graph out the wind speeds across the day. So if we go from midnight Tuesday to midnight Wednesday, this is the graph of all the wind speeds. You can see they go up and they go down. They're kind of fluctuating and everything. So then what they do is they take the average of all those values. Take the integral, the area under the curve or whatever, and you get the same idea. So they take the average for that whole day, and that would be what they would record as the daily wind speed average. So if we say the average wind speed for the day was 3 miles per hour, that doesn't mean that it was 3 miles an hour constant the whole time, because of course there's going to be times when the wind calms down, there's going to be times when it spikes and stuff like that. Okay, so it's just a daily average. If we're looking at this data like it is here, we can only look at like a week at a time before it gets really busy. You can kind of see when the storms come in and when we have low pressure, and then that sucks the storms in, because nature abhors a vacuum, as we learn in physics. So essentially what's going on here looks pretty busy. This is actually a time plot. So as time goes on, we're graphing out the average wind speed for that week. Okay, so that's what we're dealing with. Here we have the daily average wind speeds graphed out for an entire year. So over here we have the number of days, and then we have our average wind speeds. So there were some days where anywhere from 0 to a half a mile an hour, from half a mile to 1, but not including 1, going all the way up to some day where we had a maximum of 8.67. Over here we have our 5-number summary. Okay, this is what it takes to be able to create a box plot. And when you graph out this information, it's graphed out on a box plot. And it's actually nice to put a modified box plot. And it's called modified because it shows outliers. Okay, if it wasn't modified, it would just go all the way to the maximum without doing the left and right fence. Okay, but we always use modified box plots. Anyway, so whenever we graph out this information, we have our maximum, we have our minimum, our first quartile, our second quartile, third quartile, and then this right here is going to be the furthest point on the right fence before we have outliers, and then every point that's beyond that is going to be considered an outlier. If you notice here the difference between the dot and the asterisk, what that's telling us is that this is just a normal outlier, which is more than 1.5 times the interquartile range. And this is called a far outlier because it's more than 3 times the interquartile range from the third quartile. Okay, so anyway, this is definitely a far outlier, and you might be curious why there was a day with such a crazy high wind speeds, and we'll actually go into that later. So just looking at the shape of the distribution altogether, how many modes do we have? So what would be the most frequent category, or what would be a typical day? On a typical day, what would we expect our wind speeds to be for the entire year? Well, it looks like our mode's going to be kind of in this category here. So we would expect anywhere from a half a mile an hour average to a 2.5 mile an hour average for that year for this location. It looks like that's kind of our mode here, but our interquartile range is actually from anywhere from about 1 to 3. So we could say it would be pretty typical to have anywhere from 1 to 3. Our data is clearly skewed to the right. You can't get any less than 0, but it can always get windier. And so these values here, including these outliers, are going to skew our mean to the right. So if we were using summary statistics to describe the range and the spread and the center, we would use the median and the interquartile range. Our median is given here. That's our 50 percentile mark, which is a 1.9, which is not impacted by our outliers, right? And our interquartile range, which would be Q3 minus Q1, that's going to be the box here, Q3 minus Q1. That would give us the measurement for our spread instead of using standard deviation. All right, so instead of just looking at the entire year, what would be kind of fun is if we broke it down into two different categories. So the spring and the summer and the fall and the winter. So do we expect to have different weather depending on, well, different wind speed, daily average wind speeds depending on that? So we can compare these two pretty easily. The first thing we want to do if we're comparing distributions is make sure that they're scaled the same. So our Y scale, if you notice going up to 40 days, that bin height here going up to 40 days is exactly lined up. Okay, if we shrunk one of them down or blew up the other one and they weren't the same, then it would be comparing apples to apples, and it would kind of make the data look different. Okay, so we want to go ahead and make sure that's lined up. The other thing was kind of nice is we can look at these side by side like this, but if I drag this one over here, and so it started out at 0 here, it makes it really easy to compare them because you can see exactly when it starts to differ. So if we're looking at fall and winter, it looks like those are going to be windier than the spring and the summer, right? So the mode for the spring and the summer is going to be calmer, about anywhere, I guess, from 1/2 to 1.5, right? But the mode for the fall and the winter looks like it's in the middle, around 2 miles an hour for an average wind speed. Also, you can notice that we have our higher wind speeds are definitely going to be in the fall and the winter, including our crazy day, whatever that day was special about that day, that far outlier, that was occurring during the fall and the winter as well. Here we have our 5-number summaries, sorry, not 5-number summary, just summary statistics. In each one of these, the mean, standard deviation, median, and interquartile range, those are statistics from the data that we're gathering. So it's just a summary of the data. So here we have a difference in average of I'm going to go ahead and, so 2.71. So the average daily wind speed is going to be 2.71, where for the spring and the summer it's 1.56. So you can see it's much higher for the fall and the winter, but that also for the fall and the winter is going to be highly impacted by this outlier, this day where we had almost a 9 mile an hour average wind speed. So we really should not trust the mean for the fall and the winter, and we really shouldn't use the mean for the spring and the summer because it's going to be skewed by since the data is skewed, it's going to be drawn to the right as well. So we should not use the mean because these are not unimodal and symmetric. If it looks something more like a bell curve like that, then we could use our mean and standard deviation. Wow, I can't just help myself. But anyway, we'll get into that. That'll be our next chapter. So I think we'll probably have a quiz that I'll have you guys do, just a take-home quiz next week, and we'll do some review. And then we'll start the bell curve and standard deviation and z-scores and all the good stuff, which is a huge underlining theme that you'll have recurring throughout the entire year. So it's really, really important. All right, so again, the reason we can't use the mean, same reason we can't use standard deviations, because these deviations from the mean are going to be so large, this is not going to be an accurate measurement for the spread for either one of them, because this one is skewed and this one is skewed and also has outliers. So either one of those would not work. So we want to use the median and the interquartile range. Which one has a higher median? The fall and the winter. So the 50 percentile is going to be higher than the 50 percentile, which we would say would be a typical day. Because half the days were windier and half the days were not as windy as that day. And the interquartile range is going to tell us that the fall and the winter has more spread, which means the data is more spread out. And you can even see that, right? So it's kind of clustered all together and fairly tight when we're dealing with spring and summer, but with the fall and the winter, it's much more spread out. And the median and the interquartile range are not going to be impacted by this outlier because the middle 50% is still the middle 50%, regardless of what the 100 percentile over here is doing. Okay. Same thing with the median. The middle 50% is going to be the same, regardless of what's happening on the ends. Okay. That's why the median and the interquartile range is the best way to summarize this data. Another way, instead of just breaking down by season, we can break it down by month. So here we have 12. Now, if we looked at 12 histograms and we stacked all 12 of them together, even if I use 12 different colors, any idea how busy that's going to be? So if we're just comparing 2 histograms together like we are here, that's totally fine. But as soon as we start getting into multiple histograms, even more than 4, you're going to want to look at a summary of the histogram. And if you think about it, this general shape here could be described by a box plot, right? Oh, I totally did that wrong. Let me just redo it. So if I drew box plots for these, it might look something like this. So here's the interquartile, and then we got a tail going out to here, and our median's probably going to be there, and then we have some possible outliers here, right? This is a summary of our histogram. Okay, it's always better to have the actual histogram, but the summary is quicker and easier to see. Okay, and from it you can even see that it's skewed because the right whisker is longer than the left whisker, right? Also the median looks like it's going to be closer to this side as well. So, and also the outliers are clearly seen in the modified box plot as well. If I did something for the other one, it would be much more like this. And so still slightly skewed to the right, but if you notice, it's more evenly distributed here. Maybe this would be even further out to the left, okay? And we would have a far outlier, maybe an outlier or two over there as well. So here we have a bunch of box plots, modified box plots, which is helping us summarize from January all the way to December. What I do want to show here, the blue one, the reason it's different is the blue one actually comes from this right here. Okay, that's the overall for the entire year. Okay, so keep that in mind when we're looking here. So if we looked at the whole year, we have all these values here. They were all outliers for the entire year, but some of these days here might have been unusual for that particular month. So first of all, just looking at these box plots here, what trend do you see? Just as a general trend. It looks like it's pretty high and spread out, and then it calms down and lower, and then it starts getting even higher again, right? So during the spring and the summer months, except for April and May, you know, we have really high wind speeds in Oklahoma because that's our tornado season, right? Besides those 2 months, in June and July, especially July, it's incredibly calm, and it's also incredibly consistent. Look how tight the maximum and the minimum, at least to the right fence, and the interquartile, look how tightly close together that is, right? So it's very consistently calm. Looks like almost every day except for one day had an average that was under 2. I can actually, yeah, anyway, so almost every day except for one had an average that was below 2. So that was a very, very calm day, or a very, very calm month. I can actually move this down, I think. Yeah. All right, so if I go to 2, it makes it easy to see. So there was one day that was considered an outlier that was just over 2 miles an hour for that day. But that 2 miles an hour would not have been unusual for the entire year. So if we only broke it down by year, that would be even within the interquartile range. That would be just another typical day. But it was an unusual day because it was an unusual day for July. And so that's why we can get even more information when we break them down by groups or by months, by summer and spring, or sorry, summer and winter months, or whenever we look at them by month as well. Okay, so this 5.5, which I put right here, the reason I put this red line for the 5.5 here is because that was what was considered the right fence for what would be considered an outlier for the upper bound for the entire year. So anything that's below that would be considered typical. So if we look at these points here, here, and here, those 3 are considered outliers for their respective summer or spring months. But for the overall year, they would not have been considered unusual. So these are all data that would have gotten lost if we only looked at a summary of the entire year instead of looking at it month by month. Okay, just some other questions we can ask here. Oh yeah, by the way, we can see our crazy outlier here. That was in November. So interesting. And there were a few other outliers that happened in November. If I ask just general questions, which month had the highest typical wind speeds? So if I'm just looking at the boxes here, which one of these boxes looks like it's the highest? So it looks like it's either going to be January or March. And if I wanted to compare January and March, it looks like their medians are about the same. The maximum values, though, were higher for January. If I wanted to compare January and March, which one had an overall spread? So which one had more variability in the amount of their wind speeds? Or which one was more volatile in the total range of different wind speeds that we had? Then we would have to say that would go to January. Which month had the widest range altogether? So it looks like our widest range is still going to be January. Okay, so January is kind of all over the place, and it's a pretty windy day, or a pretty windy month as well. Which one was the most consistent or had the least amount of spread? That would clearly be July here. Which one looked the most skewed? So we can actually, a better question, which month had data that looked symmetrical? So if I'm looking for symmetrical data, I'm looking for, in the interquartile range, I'm looking for the median to be balanced in between those two. And I'm also looking for whiskers that are about the same length. So this one looked like it's slightly skewed to the right, but it looks more or less symmetric. We could probably get away with using a bell curve for that one. And there's no outliers. This one, kind of the same thing. The interquartile range looks pretty even here, but it's a little longer on the whisker. Actually, look at July. July might be the most symmetric. We can see the median is slightly closer to the low end, so it might be skewed a little bit to the right, and it does have an outlier, but this one is pretty symmetrical. I don't see, looks like March looks like it's fairly symmetrical as well. Which one is the most skewed? That's a good question. Well, there's definitely a lot of outliers going on with November. If we look at October, the interquartile range was really close to the minimum, but there's a really long whisker here. So the imbalance between the whiskers, it looks like that one's probably going to go to October. September is pretty bad as well. So September and October are probably the ones that are the most skewed. Anyway, so lots of different questions you can ask here. And this was an overall outlier for both November and for the overall year. All right, so the question we have is, what do we do with outliers? So here we have, this is just November's graphed out, okay, so we can kind of go into just November and see what's going on. There was that one day that had a wind speed about 8.6 miles per hour. Was that considered unusual for November? Yes, we said it was. And the question when we have outliers is we need to make sure, was this an error when we entered the data? Is there a reason we can explain this outlier? Was this outlier an anomaly? Would we typically expect that occurrence to happen every November? Is this going to mess up our statistics and make November seem like it's something that it's not? Was this kind of like a once in a lifetime event? And so one of the things that we could happen, like for instance, whenever I asked student height, somebody told me 170. Well, if it's 170 inches, that would mean they were 14 feet tall. It's taller than Goliath. He was like 9 feet. So probably not what they meant. They probably did not mean 170 inches tall. They probably meant 170 centimeters, which would end up being about 5.5 feet. So that's what I would go with. So if I had a crazy outlier, could it be that whenever I was entering the data, I was using the wrong units, or somebody who answered the survey was using a different units than I was? Clearly the person's not 14 feet, so I can go ahead and change that to 5.5 because I understand what happened. Or was there an extra zero added? Kind of like the problem we had with the mistake, right? When we add an extra zero from 200,000 to 2 million. So same thing there. And if we can fix the outliers, that's great. Go ahead and fix them so that they're no longer outliers. You always need to, whenever you're publishing your results or your report or whatever, if you omit the outliers or if you fix the outliers, you always need to be upfront about what you did. So don't try to hide it. If you hide what you do, then that's kind of some shady practice, and that's frowned upon. So it is okay to omit outliers if you believe that they are not representative or that it's going to mess up your overall analysis. For if we really wanted to know what we could expect to happen in November, we might remove this point because that might have been a once in a lifetime event. For example, this is what actually happened on the day. So November 22nd, 1989, wind, snow, cold gives Northeast a taste of winter. So an intense storm roared like the Montreal, I should know that, expressed through New England yesterday, bringing frigid winds up to 55 miles an hour. So at certain points it peaked at 55 miles an hour. So the average for the day, because it wasn't 55 the whole time, averaged around 6.8. 2 feet of snow in some parts of Vermont, and a preview of winter after weeks of mild weather. So typically they're saying we do have mild weather, but all of a sudden this was just a crazy day, just kind of like a perfect storm type thing. Residents throughout the region woke yesterday to an icy vortex that lifted an airplane off the runway,
and Newark, and made driving dangerous in New England because of rapidly shifting winds. There you go. That seemed to come from all directions. So this was just an insane anomaly, just a crazy day. Might be, it might be 10 years until we have a day with such high winds like that. Let's not relate to like a hurricane or something like that. So is that typical behavior for that month? Probably not. So we should, if we were going to analyze what was going on in November, we should probably remove this outlier and analyze what would normally happen in November when we don't have some crazy weather like that, right? Because otherwise it's going to mess up our analysis of the data. All right, so that's it. About 20 minutes, not too bad. If you want to get out your assignment, we're going to go through 2 problems together. Then you're going to do the rest on your own. So on number 5. Pizza prices. A company that sells frozen pizza to stores in 4 markets in the United States, Denver, Baltimore, Dallas, and Chicago, wants to examine the prices that stores charge for pizza slices. Here are box plots comparing data from the sample stores from each market. Do prices appear to be the same in all 4 markets? So here, because we're looking at more than 2 histograms here, or more than 2 plots of data, we're looking at these side-by-side box plots. Which are just summaries of the data instead of actually seeing the data itself in a histogram or even a stem and leaf plot. So on this one, we look at Denver, we look at Dallas, and we look at Chicago. Don't those look really similar? Like their ranges are about the same from the max to the min, okay? Except the outliers we have in Chicago, right? The interquartile ranges are very close, right? Looks like Dallas is the most consistent. It's the least amount of spread, okay? Denver is only slightly more spread out than Chicago and Denver. And then Baltimore, if we look, the entire interquartile range here is going to be above. It's going to be above Denver, it looks like. So in general, which one has the most expensive pizza? So if just a typical pizza you were buying in one of these 4 markets, you would expect it to be more expensive in Baltimore, even though Baltimore had some low outliers, okay? All right, do prices appear to be the same in the 4 markets? No, Baltimore looks more expensive. The other 3 markets look about the same. So you should expect to pay more for pizza in Baltimore, but the other 3 markets seem to be very similar. There's also more variation in price with Baltimore than the other 3 markets. Okay, does the presence of any outliers affect your overall conclusions about prices in the 4 markets? So we do have outliers, low outliers for Chicago. There's 1 high outlier for Dallas, but that's not really like an outlier because it's just barely above it, right? So if this was spread out, think about it this way, because we calculate a right fence by the interquartile range times 1.5. So if our interquartile range would just spread out a little bit more, this one would no longer be considered an outlier, right? Because it would increase the upper fence as well. So that's not really that big of a deal. It's really just kind of telling us that how consistent the rest of the prices were. They were all really close together in Dallas. The middle 50% of all price ranges were all really close together, okay? Kind of the same thing happening here, but we do have some, maybe even a far outlier down here, it looks like. So Chicago, there was some places that were just really cheap, but typically most of them, the middle 50%, were still really tight together, really competitive pricing. Same thing going on with Denver. There were no outliers. But the question we were asking is, did the outliers change our overall view of what prices we would expect in these different markets? Well, unless you actually went to a store where they had one of those outlying prices, in general, the middle 50% is really consistent. And the middle 50% of Baltimore is almost entirely above the other 3. So these outliers are not really going to change the overall story that's being told. They would, of course, skew the means and standard deviations, so we can't use means and standard deviations, but they're not going to change the analysis of our results here. So there's some low outliers in Baltimore and Chicago, high outlier in Dallas, but they do not change our conclusions. If we calculate the average pizza price, okay, instead of using the median, the outliers might lead us to believe that we should pay for less for pizza in Baltimore due to these outliers. So it might lower that and make us think that it was lower than what we would really actually be paying, which would be the median price, more than likely. In Baltimore and Chicago, due to the low outs, especially Chicago. Chicago would actually skew the average price for Chicago would be cheaper than everyone else, when that wouldn't tell the true story, because we're actually going to expect to pay about the same for the interquartile as Chicago and for Denver. All right, number 8, camping. Here are summary statistics and histograms for the number of campsites at public parks in Wisconsin and Vermont. What state would you say typically has more campsites available at their parks? What statistic would you use to represent typical campsite? So looking over here, here we have Wisconsin, here we have Vermont. Just looking at the overall general shape, it looks like this is more tightly clustered in Vermont towards the low end, where we have a little bit more spread going on in Wisconsin. Wisconsin also has this mode here where the most likely thing that you're going to find if you go to a park in Wisconsin is actually going to be that there's no campsite, no camping, or maybe only one campsite. Actually, if we break these down, it looks like they're broken down in tents. So this is going to be anywhere from 0 to 10 campsites. So really small parks are not a lot of camping. All right, so which statistic would we use? Well, we're not going to use the mean because both of these are skewed to the right, and we definitely got some outliers going on in Wisconsin. So we're going to use the median instead. So the median for Wisconsin, so the 50th percentile, right? So half of the parks had more campgrounds and half of them had less. That middle value from the median, which is not impacted by these crazy outliers, which would skew our average, is going to be 60 for Wisconsin and 43.5 for Vermont. So if we had to say, if we went to a typical campsite in Wisconsin or Vermont, which state would we expect to have more campsites? We'd have to go with Wisconsin. Give the appropriate statistics to describe, and when we're asking appropriate statistics, that means don't use mean and standard deviation when our data looks like this, right? That's what I mean when I'm saying appropriate. Describe the center and the spread of the distribution of the campsites. Okay, so for Wisconsin, our mean our median was 60, and the interquartile range we're going to get by subtracting Q3 and Q1. So just subtract those two, and then for Vermont, our median is going to be 43.5 for the center, and the interquartile range again is going to be 50. Just subtract those two. Do we have any outliers, and how do we know for sure? So this is where we use our right fence and our left fence. Clearly, we're not going to have any outliers on the left fence because we can't have anything that's negative. We can't have less than 0 campsites. So we don't even really need to check the left fence. It's really the right fence to see which one of these are actually going to be outliers. So to do that, we do the third quartile plus 1.5 times the interquartile range. So our IQR for Wisconsin, so I did a subscript W, is going to be 94. So 94 times 1.5. Then add that to 108, which is going to give us a right fence or an upper bound or an upper limit for an outlier in order for it not to be an outlier is 249. So that's going to be this blue part right here. And then for Vermont, that's going to be right here, which is going to be 153. So any points that are beyond 249, like these 3 data points here, 1, 2, 3, are all going to be represented by the asterisks here, which tells us they're outliers. And all of these that are beyond the 153, these 3 data points here are outliers as well. And the last thing we want to do, and how do we know? It's because they're beyond our right fence. Draw a modified box plot above the histogram. So this is a pretty typical thing we do. So you have the histogram, but we don't want to summarize it with a box plot. So you'll graph out the minimum, and then the first quartile, the median, the third quartile, and then this is going to go to our maximum point, our furthest point. The whisker goes to the furthest point that's not considered an outlier. Anything that's beyond that point or beyond that right fence, which we said was 153 for Vermont, is going to be marked with an asterisk or an X or a dot, whatever you want to do. It doesn't really matter. All right, then with Wisconsin, you're doing the same thing. The red here, I was showing you a far outlier. So 1.5 times the IQR, that's going to be whenever we're dealing with just a regular outlier. But if we do 3 times the interquartile range, which is going to be twice the 1.5, that's going to be this red line here. Anything that's beyond that is going to be a far outlier. So you could actually use a different asterisk or something like that, or you could use X's for it or something. It doesn't matter like how you want to just do it. Just make sure that you show that those are different because they're considered far outliers. That is if you even want to do far outliers. Some stat books don't even mention far outliers. And that's kind of the thing with statistics. There's a lot of variation. It's kind of a funny word, but there's a lot of variation in the vocabulary that we use. Typically, like even when I went to the AP Summer Institute over the summer, he was reading from a different textbook, so he would have different terminology for the same things. So I knew what he was talking about. I understood the concept he was talking about, but he would use weird words and that I wasn't used to hearing because the authors of our book use different words. So anyway, and when they grade the AP test, they understand that there's many different statistics textbooks. I think we have the best, but he would say something different. I think our book is the easiest to read and has the best problems in it. But our book talks about far outliers, others don't. So when they're grading the AP test, if you do or you don't, they'll know what book you're using. It's kind of funny, but you don't have to worry about it too much. All right, so that's it. I think that's the last one I'm doing with you. Yep, so work on the last ones on your own. If you signed up for a time to come to the school, I'll meet you outside the front office, so you don't even need to come into the building, and I'll bring you your textbook and your calculator. And just make sure you hit me up on Remind so that I can have it ready for you. We can't do it but from 11 to 12 because I have live office hours with geometry, and then from 1 to 2, of course, I have live office hours with you guys. So if you're struggling with any of the homework, we can literally go through all the homework problems that you want during our live office hours, and I can reteach stuff as well. So join us. That'll be good for you. And I hope you guys have a good day. It's almost Friday.